Social Science. Sir is also a coordinator, UGC, SAP, DRS 3. Sir is also a head, AISC. Sir has done his senior fellowship from ICSSR. Sir has been member of various committees to his credit. At the national level, he has been serving as a member of governing body, Inter-University Center for Teaching Education, Banaras Hindu University, Varanasi. Sir is a member of UGC Expert Committee for DNE University, Punjab. Sir is a member, Departmental Advisory Board, Department of Teacher Education, NCERT, New Delhi. Sir is also a member and coordinator for NAC peer team visits. Sir is a member in the Subject Expert Committee of UGC. Sir has 69 research publications and 7 books published to his credit. Sir has been keen in guiding 18 research scholars under his supervision. Sir has been a resource person for more than 150 plus programs. Now I hand over the session to Sir to enlighten us on today's topic, that is non-parametric test. I hand over the session to you, sir. Thank you, sir.
Okay, madam. Thank you. Thank you so much. And let me first of all thank the college authorities, especially Lalita madam and Dr. Renuka madam, for giving me this opportunity to have academic interaction with a very prestigious institution affiliated to Osmania University, Hyderabad. I will be taking non-parametric statistics, in particular, one particular test, which is known as Kruskal-Wallis test. And I will be sharing my presentation with you shortly, but I would like to request you all, if you have any query during the presentation, you may write it in the question and answer box or in the chat. After the session, we will have discussions, but if I feel that the question should be taken up right away, then I will respond to the question even during the presentation. So all of you are requested to listen carefully, and if you have any query, then you can put it in either question answer box or chat box. So with these introductory remarks, let me share a screen with you all. See, I have just 1.5 hours, and the topic given to me, I usually take 2 sessions, but I have left certain things, I have omitted certain things and focused on certain other things, looking into the fact that most of the audience may comprise of research scholars. Therefore, I have taken up those aspects or those issues which concern research scholars. So let me present the screen and share my presentation. I hope it is visible to all of you.
Yes, sir, it's visible, sir.
Okay. Thank you. Now, as you see, the topic is non-parametric tests. Okay, and in particular, Kruskal-Wallis 1-way ANOVA by RANDS. So I begin with an overview of this session, and I present you my agenda for the session. Now we have, first of all, some salient characteristics of non-parametric tests. Okay, with just one slide. Next, I will be taking up characteristics of Kruskal-Wallis test. Kruskal-Wallis test is the chief content for the day. Then, what are the assumptions that underlie Kruskal-Wallis test, and how these assumptions can be tested using SPSS. I do not know how many of you are aware of SPSS, but I will use this and show you how the assumptions of Kruskal-Wallis test are examined. Then we will take up Kruskal-Wallis test proper through SPSS. And in SPSS, there are two options. One is independent sample option and another is legacy dialog option. So we will be looking into both of these. Then we conduct post hoc analysis. Post hoc analysis is analysis done following significant results. Suppose there are significant differences among groups, then to identify the pairs of groups with significant differences, we perform post hoc test. Then I will be referring to Kruskal-Wallis test through legacy dialog option. And finally, there is a new concept known as effect size. It tells you what is the size of the effect, how important practically is the treatment which you have given, or the factor whose effect you are seeing on the dependent variable. So this is in brief an overview of the presentation. Now I begin with first characteristics of non-parametric tests. Now non-parametric tests are statistical tests that work with, okay, but not restricted to ranking or categorical data. Okay, parametric tests are statistical test of hypothesis, okay, which test hypothesis, and they are used when your data is on interval scale or ratio scale. Interval or ratio scale. They cannot handle data which is on ordinal scale or nominal scale. So these are scales of measurement inferior to interval or ratio scale. Parametric tests, they cannot handle this particular data, ordinal and nominal scale. So non-parametric tests are tests, okay, which can handle ranking or categorical data. Nominal scale is also known as categorical data or classificatory data. Therefore, tests which can handle ranking data or categorical data, they are non-parametric tests. But that does not mean that they cannot be used when the data is on interval or ratio scale. Okay. So non-parametric test can be used on any scale, nominal, ordinal, interval, or ratio, depending upon certain tests. They require at least ordinal scale. Some other tests they require nominal scale. For example, this particular test, this requires at least ordinal scale. Okay, next is these are non-parametric tests. They are tests with weaker and fewer assumptions. Well, parametric tests are based on certain assumptions. For example, one assumption is assumption of normality of the distribution. The underlying distribution should be normal. This is the assumption underlying parametric tests like t-test, one-way analysis of variance, regression analysis, factor analysis, and all parametric tests. They are based on the assumption that the distribution should be of particular type and most frequently normal distribution. Tests which are non-parametric, okay, there is a myth that they do not have any assumption, and this myth should be busted. Today itself, we will find that the Kruskal-Wallis test has also certain assumptions, but these assumptions are weaker relative to parametric test. They are weaker assumptions, and their number is also sometimes less. So non-parametric tests, okay, they are not as stringent as far as assumptions are concerned as parametric tests. Next is they can work with. but not necessarily restricted to small or very small sample. Normally, parametric tests, okay, they demand a certain size of sample, moderate sample they require at least. Okay, they do not work well with very small or small samples. Why? Because when the sample is very small, there are chances it will not be representative. Okay, and the assumption of normality, etc., will be violated. But non-parametric tests, they can handle small or very small samples also. Why? Because their assumptions are weak. Next is non-parametric tests are alternative to the parametric test in case of assumption violation. Okay, so if you have data, strong data, okay, interval scale or ratio scale data, but you cannot use t-test or analysis of variance test or regression analysis because the assumption of normality is not satisfied. Then you have an alternative, and that alternative is non-parametric test. But every parametric test, okay, does not have a non-parametric counterpart. We must keep this in mind. Some tests may have non-parametric counterpart, like one-way ANOVA has non-parametric counterpart, t-test has a non-parametric counterpart. Okay. Now, another myth associated with non-parametric test is that they are not powerful. And this is wrong to believe that non-parametric tests, they are not powerful. Powerful means power is ability to reject H0 when it should be rejected. So rejecting false H0, okay, is nothing but power. Power is the ability to reject a false null hypothesis. If null hypothesis is not true, then the test should be able to reject it. And it is believed that the non-parametric tests, they are not able to reject null hypothesis when it is false. But this is not correct. Okay, the power of non-parametric tests is almost equal. They are almost comparable with parametric tests, provided the samples are not too small. If samples are very small, then probably non-parametric tests are less powerful than their parametric counterparts. So if your sample size is not very small, suppose sample size is 20, 30, then the power is comparable. And lastly, another myth is that whenever you have non-random sample selection, then go for non-parametric test. I don't think this is a correct interpretation, correct perspective. Non-parametric tests, they also require unbiased, preferably random samples, because they are also generalizing from sample to population. Okay, therefore, they very much require a sample which is representative of the population. Otherwise, there will be no logic in generalizing the results from sample to population. So these are basically the some major characteristics of non-parametric tests. So non-parametric tests, they can be used at lower levels of measurement. Okay, they are good alternative to parametric test. Whenever the assumption of parametric test, they are violated, they are not met, then we can use non-parametric test. Now I close this discussion and go to specifically the test which is Kruskal-Wallis test. So we now take up Kruskal-Wallis test. Kruskal-Wallis test is a K samples non-parametric comparison test. K sample means K is generally whenever there are more than 2 samples, we say K samples, more than 2. Okay, 2, whenever there are 2 samples, Okay, we call it two sample test, and when there are three or more, okay, then we call it k is greater than or equal to 3, we call it k samples, more than two samples, 3 or more samples. Okay, so this is also a test of comparison between groups or among groups. Okay, between group is normally used when there are two groups, but when there are more than two groups, we use among. Okay, now what are the characteristics? What is in fact Kruskal-Wallis test? Okay, now Kruskal-Wallis test is also known as one-way ANOVA by ranks. So you must know what is, actually I assume that you know what is ANOVA, because it is non-parametric test of ANOVA, analysis of variance is ANOVA. Whenever we have to compare two groups, okay, group one, say for example, male and female, we have two groups, and we normally use independent sample t-test for comparison of these two groups, and we compare the mean scores of this mean one and mean two, and and take a decision regarding the difference between these two means. When samples when the groups are more than two, for example, rural, urban, semi-urban, and we want to compare their, say, some characteristics, say anxiety or stress. Okay, so there are more than two groups. Data is on interval scale, so we compare more than two groups using ANOVA, analysis of variance. Analysis of variance. So analysis of variance is K sample parametric test. K sample parametric comparison among groups. T test is two sample parametric comparison test. Okay. Kruskal-Wallis test is non-parametric counterpart of this analysis of variance. That means it is K sample non-parametric comparison among groups. So first characteristic is that it is non-parametric. Non-parametric tests are based on ranks. Non-parametric tests, they are based on ranks or frequencies. So if your data is nominal scale data, you use frequencies. Certain tests use ranks. Okay. So Kruskal-Wallis test is one-way ANOVA by ranks. It is a non-parametric counterpart of regular one-way ANOVA or parametric one-way ANOVA. And this requires ranking data. That is, the data should be on ordinal scale at least ordinal scale, ordinal or higher, not nominal. Nominal is not permissible. Ordinal, interval, and ratio. Okay. Okay with Kruskal-Wallis test. So we have one grouping variable with three or more levels. This variable, for example, residence. Okay, residence has three levels. One is rural, another is urban, third is semi-urban. So this is grouping variable or factor. Residence is factor or grouping variable or independent variable. Okay, and this has three or more levels. Here, this means level. Level means number of groups. And Kruskal-Wallis test compares several mean ranks. Now, one-way ANOVA compares several mean scores. ANOVA compares means, but Kruskal-Wallis compares mean ranks. Why? Because it is based on ranks. One-way ANOVA by ranks. Oh. So it is one-way ANOVA by ranks, counterpart of parametric ANOVA. It requires at least ordinal scale variable, and it should have one independent variable, okay, having 3 levels. And then it compares, what it does, it compares mean ranks. And it may be used when ANOVA assumptions get violated, because it is a non-parametric counterpart of ANOVA. And we take a follow-up analysis in case of significant differences. Say we are comparing 3 or more than 3 groups. Suppose there are 3 methods of reducing stress. Okay, and these 3 methods are: one is yoga, another is, for example, music, third is, say, counseling. Okay, so we take 3 groups randomly and give them treatment to reduce stress. One is given yoga sessions per day for a week, another is treated through music, and third is given counseling. Okay, after that we compare their means, mean 1, mean 2, mean 3. This is one-way ANOVA. Okay, in ANOVA we test the hypothesis that all these 3 group means are equal. Mean 1 is equal to mean 2 is equal to mean 3. If this hypothesis is rejected, that means the groups are not same as far as their mean score is concerned. Then we have to find out if where is the difference. Is it that mean 1 is different from mean 2, but mean 2 is same as mean 3? Or mean 1 is different from mean 2 and mean 2 is also different from mean 3 and mean 1 is also different from mean 3. This is known as follow-up analysis. This is done when we have found that groups differ. If the groups do not differ, we need not do anything. But if the groups differ, then we have to follow it up with some tests. So in Kruskal-Wallis test also, we can follow it up with post hoc test. Now I come to research situation for one-way ANOVA by ranks, although I have already given you situation. Suppose a researcher wish to compare 3 teaching methods in terms of achievement in mathematics. Now this is an example from my field, education. Okay, someone has raised hand, but I requested to put your question in chat. Okay, because hand is not in my hand. Organizers have to say it. So if you just write in chat or in question answer, I will take care of it immediately. Now, a researcher wishes to compare 3 teaching methods in terms of achievement in mathematics of 6th grade student. We want to see whether 3 methods of teaching are equally effective in terms of achievement in mathematics, or some particular method is better for students' achievement of class 6 students. Now for this, what do researcher has done for this? 3 random groups of 6th grade students were taught through 3 different methods of teaching. After teaching, each group was administered an achievement test in mathematics. The achievement scores violated the assumption of normality and homogeneity of error variances. Therefore, now the researcher should go for the non-parametric counterpart. Why? Because the dependent variable is achievement. This is interval scale. Okay. And there are 3 groups because there are 3 methods of teaching, right? And we have tested the assumption, normality, it does not fulfill, it is not fulfilled. Homogeneity of variance is another assumption, it is not fulfilled. Therefore, we cannot go for ANOVA. So we must go for Kruskal-Wallis test or one-way ANOVA by ranks. Okay. Someone is asking difference between one-way and two-way ANOVA. Okay, one-way ANOVA is when you have one independent variable. Independent variable is one. Okay. 2 ANOVA is when you have two independent variables. Independent variables are two. For example, we have one residence, okay, rural, urban, semi-urban, and also gender, male, female. So we have this kind of arrangement, this kind of sample. We have some persons, rural student, male, rural student, female, urban male, urban female, semi-urban male, semi-urban female. So we have two criteria of classification. One is gender, another is residential background. So this is the case of two-way ANOVA. This was the question asked in chat. So we are dealing with one-way ANOVA. Okay, we could have dealt with two-way ANOVA, this is a separate topic. Now, what are the assumptions of Kruskal-Wallis test? As I told you, Kruskal-Wallis test is used when the major assumptions of parametric ANOVA are violated. But does it mean that Kruskal-Wallis test does not have any assumption? No. This is a myth that non-parametric tests do not have any assumption. We will see what are the assumptions of non-parametric ANOVA, yani Kruskal-Wallis test. One is random sample. This also requires that sample should be selected randomly, or at least the treatment should be assigned randomly. We have to see that some samples are not biased. Okay. Now, second assumption is that the independent observations means these three groups are independent of each other. There is no overlapping in these three methods of teaching. It should not happen that one particular student is common to all the three methods. Okay, or one group is in all the three. One group is taught all the through all the three methods. It should not be the situation. So these observations, these three groups should be independent of each other. And then rankings, at least the scale should be ranking. We should be able to rank the data. If the data is not amenable to ranks, we cannot use this Kruskal-Wallis test. Then we must have three or more groups. Now these are the two assumptions. One is similarity of shape of distribution of outcome variable. See, we were having achievement data, achievement scores, okay, of class 6 student taught through method 1, method 2, and method 3. So we have these three distributions. These three distributions should have similar shape. What does similar shape means? We will look into it. And then we must have non-parametric homogeneity of error variances. Okay, what is homogeneity of variance? Homogeneity of variance is that the individual differences within these scores must be almost similar. Say, for example, these scores are 1, 2, 3, 4, 5. Okay. The second group scores are 10, 20, 30, 40, 50. Now, these two do not have equal variance. Actually, the variance of this group is 10 times the variance of this group. So they cannot be said to be having equal variance. So equal variance is if the groups are like this 1, 2, 3, 4, 5, 11, 12, 13, 14, 15. So the differences among the individuals are same, almost same. Another is 7, 8, 10, 11, 13, almost same. Differences among groups are almost same. So like this is homogeneity of variance, but we have a non-parametric version of homogeneity of variance. Now, what is the data like in Kruskal's test? The data consists of 3 groups. For example, this is specimen data for Kruskal's test. We have stress scores of senior, intermediary, and junior level employees. Okay, we have 3 kind of employees. One who are top level employees, second middle level employees, and third lower level employees, junior level employees. Okay, we give them stress test. And suppose higher score means higher stress. So we have 3 groups. In the first group of senior employees, we have 1, 2, 3, 4, 5, 6 employees. Then 1, 2, 3, 4, 5, and 1, 2, 3, 4. The groups may not have equal sample size. It may differ. So this is an example of Kruskal-Wallis test because the samples are small. So probably we cannot go for parametric ANOVA. We have 3 groups, okay? And we have stress scores. Stress scores is interval scale data, okay? But you can rank it. Interval scale data can be converted into ranks. So this is a fit example for Kruskal-Wallis test. Now we come to the testing of assumptions. Before applying Kruskal-Wallis test, okay, we must see whether the data fulfills the assumptions of non-parametric ANOVA. Now there are 2 assumptions which are to be tested statistically. Other assumptions are, they can be seen that they are fulfilled from here. 1, random sample. These three groups have been taken randomly. Number 2, independent observations. This person A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. So all these individuals are different. Therefore, these are independent observations. And third, the dependent variable should be ranking scale. So this is interval scale data. So definitely it is ranking data. Therefore, these assumptions are met. Okay. Now, what about the similarity of shape and non-parametric homogeneity of variance? These 2 are to be tested statistically. So there are ways to examine these assumptions statistically. And I will be showing you examining these assumptions through the software SPSS. Now let us take example of data. Okay. This data, I have a hyperlinked one data. And this is entered in SPSS. Say, we have here achievement. You see here ACH, achievement, and this is residence. So residence is rural. Okay. So we have 22 up to this rural students. Okay. Then again 22 are urban. This is up to 44. We have urban. Okay, 44, and then up to 66. This is equal sample. Up to 66, we have semi-urban. Okay, so there are 22 rural, 22 urban, and 22 semi-urban students, and these are the achievement scores of these students. So data has been entered like this. There are 2 variables. One is dependent variable achievement. Another is independent variable residence. Sample size is not small. 22 is okay. We can go for parametric ANOVA. But for parametric ANOVA, distribution should be normal. Okay. So let us first Yes, all groups have same sample size here. So how to check normality? Okay, we check normality through this analyze, descriptive statistics, and explore. Analyze all statistical tests, they are here. Analyze the data. Descriptive statistics, explore. Explore means explore the nature of the data. This is a dialog box. It asks you what are your dependent variable and independent variables. By dependent variable is achievement and independent is resilience. Okay, come to this plot. The stem and leaf, we don't need it here. You check histogram. Histogram will tell you the shape of the distribution and normality plot with test. Continue and OK. So it has applied this statistics. Okay, this is the first table. It gives you mean, median, variance, standard deviation, skewness, kurtosis. Okay, the shape of the distribution is normally given by checked through skewness and kurtosis. Okay, skewness here is minus 0.926. In the second case, it is 0.999 minus. In the third case, it is minus 0.926. So all three are negatively skewed, okay, and almost to the same extent. Test of normality are here. These I have already pasted on my this. Say these are two tests, Kolmogorov-Smirnov test. This one is interpreted when sample size n is greater than 50. Greater than equal to 50, and this is interpreted when n is less than 50. So we interpret this Shapiro-Wilk statistics. Okay, we do not touch this. Now there are three tests for rural, for urban, or for semi-urban. So for rural, the value of test statistics is this much, degree of freedom is this much, and significance is this much. Now I assume you know how to interpret it, and the way to interpret is if significance is less than alpha level, significance level, alpha level, then it is called significant result. Less than or equal to. If it is greater than alpha, then it is not significant. So in this case, if your alpha significance level is 0.05, then because this value is less than alpha level of 0.05, therefore this is significant. Similarly, this is also less than 0.05. This is also significant. And this is also significant. All these three are significant. It is clear from table 2, the distribution of achievement in commercial mathematics of rural, urban, and semi-urban students are non-normal, as each of the p-values, this is also called p-value, probability of significance, is smaller than 0.05. Therefore, the achievement score for rural, they are not, because whenever this is significant, H0 is rejected. And what is H0? H0 is the distribution is not different from normal. So we have to reject it. We cannot assume that distribution is not different from normal. We have to infer that distribution is not normal. Therefore, we cannot apply ANOVA is out of question. Parametric ANOVA cannot be applied. Therefore, we must go for non-parametric ANOVA. But non-parametric ANOVA or a one-way ANOVA by rank, this requires that shape of the distribution should be same. Now, shape is to be seen through this histogram. So if you see this output and you further scroll it down, you will find these histograms because we checked histogram. So this is histogram for rural, urban, and semi-urban. Okay. Now, if you look into the shape, as you all know, the normal distribution is something like this. The peak is in the middle in normal. Here it is towards the right. The peak is towards the right. Okay, and tail is on the left. Therefore, this is negatively skewed distribution because tail is on the left and peak is on the right. And you have also seen its skewness was minus 0.996, something like this. Similarly, look into this histogram. This is also peak is on the right and on the left side, the height is decreasing gradually. So the tail is on the left. So distribution is something like this. This is negatively skewed distribution. And third distribution is also like this, negatively skewed distribution. Therefore, we can now interpret the three histograms give an idea about the distributions. Each one of the distribution is negatively skewed to the almost same extent. Most of the scores are on the upper side in each of these three distributions. Therefore, the assumption of similarity of shapes does not seem to be violated. Okay, we can assume that these three distributions are having similar shape. Now the box plots, these are also checked for further going down into the output. You will find these box plots. These are the three box plots. They also tell you about the shape of the distribution. And they have almost similar shapes. Why? Because this is known as upper whisker. Upper whiskers are small as compared to the lower whisker. In all these three distributions, lower whiskers are long, upper whiskers are short. Okay, this line is almost, this line is median line. Median line. Okay, the position of the median line in the box is also almost similar. Therefore, it looks like the distributions have a almost similar shape. Therefore, we can assume that first assumption is, someone is asking that please repeat the interpretation. Interpreting box plot. As observed from the box plots, all the three distributions are top heavy. The median line in each box is towards the upper side of the box. The upper whiskers are small and the lower ones are elongated, suggesting negatively skewed distributions. The assumption of similarity of shapes looks pretty satisfied. So first assumption we have checked, and it is that the shapes are similar. Now let us come to the next, and it is equality of non-parametric variances. Now for this we must know what is parametric variance. Parametric variance is, okay, you will find from here. Let us look into this. This is one article I have hyperlinked. A new non-parametric Levin's test for equal variances. So new non-parametric See this. Okay. So see, this is homogeneity of variances. Widely used hypothesis for test of equal variances is H0 sigma 1 square is equal to sigma t square. That means two variances are same, two or more than two. And H1 alternative hypotheses are they are unequal. Now, ANOVA is, as a reminder, the mean version of Levin's test is this: ANOVA on xij minus xj bar absolute value. मतलब ANOVA, parametric ANOVA, when you subtract from each score the mean of this and take its absolute value and take ANOVA on this. This is what is parametric ANOVA. But in non-parametric ANOVA, you have, instead of mean, you have mean ranks. If in parametric ANOVA, we take the absolute deviation of each score from mean. But in non-parametric ANOVA, we take absolute deviation of rank. Rij is the rank. Using our earlier notation, non-parametric Levin test can be written as ANOVA Rij minus xj bar r, wherein a one-way analysis of variance is conducted on the absolute value of the mean of the ranks for each group, denoted by xjr bar, subtracted from each individual rank Rij for individual I in the group. Means, this means, in simple terms, this means, yes, someone is asking, do we need to interpret through graph in this test? Through graph, we are examining the one of the assumption of similarity of shape, because we are talking about shape, so we have to depend on the shape, and shape is given by the graph. Say, what is non-parametric Levin's test? One is parametric Levin's test. Parametric Levin's test. Whenever you calculate, you conduct parametric ANOVA, you use this parametric Levin's test. Okay. And in case of Kruskal-Wallis test, you use the non-parametric Levin's test. I will tell you how. Okay. So we go to the data and I will show you how to calculate. First is, this is the same data. See, this is the data. Okay. Now we want to conduct a non-parametric Levin's test. What do? We first find rank of, we rank these scores. Okay, and this can be done automatically. Transform rank cases. Okay, you rank cases. Achievement in commercial mathematics, this is the variable we want to rank. Okay, and just okay. So this rank has been added to the data. You get here R achievement, rank of achievement. This is 85, rank of this is 56.5, 83, 50.5, and so on. Okay. This is the first step which we have conducted. Assign rank to the score of outcome variable. Transform rank cases. Second step is compute group mean ranks. Now we want to compute mean rank of the three groups. Okay. So how do? We go to data aggregate. Okay. We go to data aggregate. Okay. Here, summary of variable. In this summary, we put rank. We have calculated rank, you put it here. And residence in this break variable. And okay, you will get ranks, mean ranks. So this is the mean rank. 32.89 is the mean rank of rural. See what is mean rank? All these scores, all these ranks, okay, up to 22. Add all these ranks and divide by 22. You will get 32.89. Now add these 40, next 22, up to 44, divided by 22. This will come out to be 43.75. Third, semi-urban, similarly, add these two and find their mean. This will come out to be 23.86. So we have calculated rank. We have calculated mean of these ranks group wise for separately for 3 groups. Now we calculate the absolute difference between these two. Difference between these two without taking into consideration the sign of the difference. Absolute value of the difference between rank of achievement and this mean rank. Okay, this can be done through calculate variable, and let us define this variable as absolute deviation. Yeah. And how do we define absolute deviation? See, from here, arithmetic, you take absolute. The ABS is absolute. You click at this upward arrow, here it comes, absolute. And we want to calculate absolute deviation of the ranks, okay, from the mean rank. So I have rank minus the rank mean. See what I am doing? I am taking a difference of this rank and its mean. So rank and its mean. Okay, okay. This is okay. So you get another variable. It is absolute deviation. So if you subtract 32.89 from 56.5, you get 23.61. Okay. 50 minus 32. Say, for example, take this 22 minus 32. Okay. So it should be minus 10, but we have taken absolute. Therefore, it is plus 10.39. Now what you do, you just conduct one-way ANOVA on this. See, we have done what we have done. Okay, we have assigned rank. Then we have computed mean rank. Then we have computed deviation of the rank from mean rank. Okay, and now we have to conduct one-way ANOVA. And if this ANOVA is not significant, our assumption is fulfilled. Interpret the non-parametric Levens statistics. So last step is you conduct ANOVA on this. And how to conduct ANOVA? Analyze, compare means, and one-way ANOVA. Last variable you take here, and residence, the independent variable here. Just click OK. So this is the table. F value is 2.703 and significance is 0.075. So this one is the table here. Okay. So we have what we have done. We have calculated ANOVA F of rank of the scores minus average rank. Okay, this is F value. This is non-parametric Levens test. And because this value is greater than alpha level of 0.05, Therefore, this is not significant. So table 3 shows the non-parametric Levin's statistics is not significant at 0.05 level because F degree of freedom 263 is equal to 2.703. P value is 0.075, which is greater than 0.05. Therefore, the null hypothesis that there is no significant difference in the non-parametric error variances is not rejected. Therefore, the assumption of homogeneity of non-parametric error variance is not violated. So, assumption of similarity of shape is not violated. It is met. Assumption of non-parametric Levin's test is met. Now we can conduct one-way non-parametric ANOVA. Okay. So now we come to both these assumptions have been tested. So we can now perform non-parametric ANOVA. Now, but before that, let us see how research objective and null hypothesis are formulated for the Kruskal-Wallis test. So for Kruskal-Wallis test, we will write objective like this to compare the mean ranks of tolerance of viewers treated through lecture, film, and discussion and storytelling. Suppose there are four ways of developing tolerance. Today you see intolerance everywhere. So I want to build tolerance among people, and I want to I want to find out which method is best for developing tolerance. And I'm trying four methods: lecture method, I am giving lecture on tolerance; film, showing some short films; discussion; and storytelling. Okay. So the objective will be written like this: to compare the mean ranks of tolerance. So mean ranks of dependent variable of which groups? Of four groups, that is treated through lecture, film, discussion, and storytelling. And null hypothesis will be written: there is no significant difference in the mean rank of tolerance of viewers treated through lecture, film, this. Now we take up one example where you will find there is no difference among groups. So first I take simple example where there are no differences. Then I will be taking up another example where there are differences. So this is the first kind of example where null hypothesis is not rejected. Okay. So I go to this data and show you how to perform this test. We again have two variables. One is residence, another is social intelligence. Okay. Residence is having three levels. One is rural, another is urban, and third is semi-urban. Social intelligence, these are the scores of social intelligence. These samples are small, only 6 in each group. Okay, so we can't go for parametric ANOVA. So we go for non-parametric ANOVA. How to conduct non-parametric ANOVA? We go to analyze and go to non-parametric test. Okay. Now we have non-parametric test, one sample, independent samples, related samples, and legacy dialog. So there are two ways. One is explore this independent samples. Okay. Now go to this. This is objective. This is field. Objective and field. Go to this field, and it says what is your test field. The test field is the dependent variable, social intelligence. And here you find group. Group is on the basis of residence. Okay. And just run. So you get the output of the Kruskal-Wallis test. you have three tables. First is this one, hypothesis test summary. The distribution of social intelligence is same across categories of residents. Independent samples, Kruskal-Wallis test. Significance is 0.216 and decision is retain null hypothesis. Why? Because this value is greater than 0.05. Therefore, null hypothesis cannot be rejected. It is not significant. Here you find total N 18 test statistics. This is Kruskal-Wallis statistics 3.061. And this is again 0.216, 0.216. Next, scroll down, you find these. Okay, they will tell you about the similarity of shape. These are almost similar, although here a little bit of box is long here, second box, but the position of this is almost same. Okay, so from this, because this is to some extent subjective also. Okay, so you can interpret this. These two distributions are almost equal, but the third one, you find the median line to be on the upper side. Okay, but now we are not discussing this assumption. I am also not discussing the non-parametric homogeneity of variance. Okay, that has already been discussed, and this is the rural number of people in rural, number of people in urban. Okay, 6, 7, and 6. So this is residence-wise box plots, and these are the two tables. One is hypothesis test summary, another is independent sample Kruskal-Wallis test, interpreting the output. Now, as an observation of figure 5 shows that both the whiskers in each box plot are of about equal length, and the median line is positioned in the middle of the box, except to some extent in the third box plot. The assumption of similarity shape does not face a serious question and can be assumed to hold good. Well, there is not a serious threat, although there are differences. Now, table 4 and 5 shows the test statistics is not significant at 0.05 level of significance. Why? Because this is sometimes also called chi-square. Chi-square 2 is 3.061, P is 0.216, and it is greater than 0.05. Thus, the null hypothesis that there is no significant difference in the mean ranks of social intelligence of rural, urban, and semi-urban is not rejected. As the three groups do not differ significantly in their mean rank, no further analysis is required. Say, because rural, urban, and semi-urban, okay, they do not differ in their social intelligence. Therefore, we need not go into further analysis to identify the groups where there are significant differences, because overall there are no significant differences. Okay. This will be taken up next when we take up an example where you will find significant differences. So this is an example, second example, and here you will find significant differences. Okay. So I go to now this data. Now we have here 4 kind of researchers: JRF and net with scholarship, non-net with scholarship, and non-net and no scholarship. And this is the coursework performance, PhD coursework performance. Okay. See, we have 4 kind of students. One is JRF, second is net with scholarship, Third is non-NET with scholarship. They have cleared NET and they are getting scholarship. They are not NET, but institution gives them scholarship, and they are neither NET nor scholarship. Okay. Now look at these shapes, almost similar. The assumption of similarity of shape holds good. Box plot, yeah, okay. Now Kruskal-Wallis test. Okay. Now I have to apply. Let us now okay. We now conduct Kruskal-Wallis test, analyze non-parametric independent samples. Okay, field is researcher here, group, and coursework performance here. Okay, run. So we get the output, and output says that the significance value is 0.003. The value of test statistics is 13.791, and its significance is 0.003. Please see. 0.003, decision rejected the null hypothesis. Okay. Total N 21, test statistics, degree of freedom 3. This is less than 0.05, therefore significant. That means the four groups, they differ significantly. There are differences. Okay. Now you can interpret this. Table 6 shows summary results of test hypothesis. Null hypothesis of equal performance across category of researchers is rejected at 0.01 level. Even at 0.01 level, we can reject because this is less than 0.003 is less than 0.01. You take two level of significance. One is 0.05, second is 0.01. So it is less than even 0.01. Therefore, it is rejected. Okay. Table 7 also confirms the rejection of null hypothesis because chi r square 3 is this much, p is this, which is less than 0.01. Thus, there is a significant difference in the mean ranks of course for student of 4 categories. To find out pair of categories of research scholars with significantly different coursework performance, multiple comparison tests will be interpreted. Now look, the situation is like this. We have 4 groups. Okay, one is JRF, second is NET with scholarship, third is non-NET with scholarship, and fourth is non-NET, non-scholarship. Okay. Now all these groups, they are not same. Their performance is different. It may so happen these are 4 groups, 1, 2, 3, 4. So in this there can be 6 pairs. 1, 2, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So 3 and 2, 5 and 1, 6. There can be 6 pairs of comparison. So out of these, all 6, there may be differences in all the 6 pairs. or there may be differences in these 4 pairs and no differences in these 2 pairs. Okay, this analysis has to be done and it has to be found out which pairs have significant differences. Okay, now this is pairwise comparison and let me show you how it is done. You perform this analyze okay, non-parametric independent samples. In this, if you go to setting, okay, and yeah, here it is by default automatically choose the test between of the data, but now you customize test, okay, and here is Kruskal is one way ANOVA K sample. Select this. Here you have multiple comparison. This is the thing which we are looking for, post hoc test, multiple comparisons. Okay, all pairwise. This will compare all pairs pairwise. Run. So we get the output like this. This table is, these 2 tables in addition we find here 1 and 2. Okay, this is one table and this is one graph. So I have taken this in my presentation. This one is the table. Now it gives you all the 6 comparisons. 6 comparisons. And now you interpret it, how many comparisons out of 6 there are significant differences. First one is non-net, non-scholarship, non-net with scholarship. This is significance. Whenever you have multiple tests, there occurs an error which is known as inflation of alpha error. Inflation of alpha error. Alpha error is increased, and this corrects it. This analysis corrects this inflation of alpha error, and therefore we, in addition to significance, we have adjusted significance. This is corrected for alpha error. So we have to interpret this one. Okay. Now this is first pair. P value is this is significant value greater than 0.05. So not significant. This is also not significant. This is significant. Not significant. Significant. Not significant. So in 2 pairs, you have significant differences. Okay. Non-net with non-scholarship, non-net non-scholarship, and net with scholarship. So these 2 groups differ in their performance. And non-net with scholarship and JRF, they differ. And the same thing is shown here. Yeah. These are the mean ranks. Mean rank of this group is 6.5, 12.63, 18.08, and 6.00. The group which has greater mean rank is better in performance. Say there are 2 groups, there are significant differences in 2 groups. One pair is this one, pair 1. This is pair 1, blue one, and this is pair 2. JRF and non-net with scholarship, JRF and non-net non-scholarship. So let us see how to look at this. Okay, now looking at the third row of the table 8, it can be seen that there is a significant difference in the mean rank of coursework performance of the JRF and non-net non-scholarship researchers at 0.01 level from this table. Okay, third row, table 8, this one, second one. No, the third one. Test statistics 11.583, Z 3.237, adjusted p-value is 0.007, which is less than 0.01. An observation of the two mean ranks, figure 7, okay, reveal that course for performance mean rank 18.08 of GRF category is greater than, therefore GRF students, they have done better than non-net, non-scholarship researchers. Likewise, it can be interpreted from row 5 that GRF category of researchers also performed significantly better than non-net with scholarship researchers. The other pair of category of researchers did not perform significantly different from each other. So out of 6, 2 comparisons, 2 pairs, they show significant differences, and 4 pairs, they do not show significant differences. Okay. What are the 2 pairs? One pair is GRF is better than non-net, non-scholarship, and GRF is better than non-net, non-scholarship. Sorry, this is our first one. GRF is better than non-net with scholarship. Oh. We were here. Okay. Now, pair-wise comparison, graphical view, significant and non-significant pairs. Each node, these are 4 nodes. Each node of the figure 7 show mean rank of coursework performance for each category of research scholars. The 2 groups connected by blue lines represent significant differences in their mean ranks respectively. These 2 groups, they show significant differences. Now, let us look at another option, which is known as legacy dialog option. So I take this data and now go for another option, and that is I have these 2 variables. One is meditation, week-long meditation. A group, one particular group is treated through week-long meditation program. Another group is treated through 10 days program, and next is through fortnightly program, 15 days. So 7 days, 10 days, and 15 days, and we want to say results in terms of self-efficacy. So these are the self-efficacy scores, and these are the three groups with 3 different treatments. So let us see what happens if you if I conduct this test. Analyze. Okay, now I want to show you another option, non-parametric, and you go to legacy dialog. In legacy dialog, you come down to this is 2 independent sample and k independent sample. Okay, meditation program is our grouping variable, self-efficacy is our test variable, and define this meditation. Meditation, on the basis of meditation, we have 3 groups, 1 to 3, minimum 1, maximum 3. Okay, and okay. So you get this output. Kruskas-Wallis test. Okay, mean ranks. If you are undergoing week long, then your mean rank is 8.63. 10 days mean rank is 10.6, and fortnight mean rank is 3.5. That means 10 days program is best. Fortnightly program does not benefit much. Week-long program is also inferior to 10 days program. The Kruskal-Wallis H is 7.623 and significance is 0.022, which is significant at 0.05 level. So look at this. These are the two tables here. One table gives you the mean ranks 8.63, 10.6, 3.5, and test statistics Kruskal-Wallis H, and this is less than 0.05, therefore significant. That means all these three groups differ significantly. Okay. Okay, I have not written the interpretation. Interpretation you can write. Now, the disadvantage of this legacy dialog option is that we do not have, in this particular option, we do not have post hoc analysis. Post hoc is not there. So if there are significant differences among group like this, then independent sample option is better option, and you should follow that. Can you perform legacy dialog test once more? Okay. Okay. Say. This is the data. Analyze non-parametric and legacy dialog. In legacy dialog, you have chi-square, binomial run test, one sample KS, two independent sample, K independent sample. So we want K independent sample. So it will appear like this. So you have to supply what is your test variable. Self-efficacy is the test variable, and grouping variable is meditation. Okay. It says define meditation. So we define how many groups are there? 3. So one and 3. Okay. A Kruskal-Wallis H is by default, it has been selected. Okay. So you get these two tables. One table gives you the mean rank of each group, and another gives you the value of the Kruskal-Wallis test. And that's all. There is, say, neither the assumption of similarity of shape is tested in this particular option, nor there is any opportunity for performing post hoc tests. Therefore, this is not advisable, and you should follow independent sample option more frequently. When we use legacy dialog test, same whenever you can use either this or that. There are ways there you can perform Kruskal-Wallis test through legacy dialog and then conduct the post hoc test through independent option. Or you can apply Mann-Whitney U-test, several Mann-Whitney U-tests. Test variable and independent variable. Yes, yes. Test variable is dependent variable. I think you have written the other way around. Test variable is the dependent variable, not independent variable, and factor is the say once again. Analyze non-parametric legacy dialog K sample. Test variable is self-efficacy, the dependent variable, the variable for which you want to find mean rank, and grouping variable is the independent variable, validation. the variable on the basis of which there are three groups. Okay. Now, last is something known as effect size. Effect size means the practical significance of this. Okay, you should have medium effect size or large effect size. Okay, so how to calculate effect size for Kruskal-Wallis test? The formula is h upon n minus 1. Simple formula is h upon n minus 1. But I will show you how to calculate it automatically in SPSS. Steps for finding out effect size. First of all, we rank that variable. So rank self-efficacy score using transform option, as I told you earlier. Then analyze, compare means. There is a way to find out this. I will tell you how. And this is interpreted as R square. And alternatively, effect size is h upon n minus 1. Now let me show you how to find it out and then how to interpret it. See, this data is there. Okay. First of all, you rank this self-efficacy. So transform rank cases. Okay, self-efficacy. Okay. So it has been ranked. This is the rank of self-efficacy for. This is rank 1. Smallest one is given rank 1. Okay. And highest score 13 is given highest rank, that is 14. There are over in all 14. Now what do we do? Analyze. Okay, descriptive statistics. Okay, descriptives. No. Analyze. Compare means. And supply here the rank as dependent variable and independent variable is meditation program. And go to option. And here you find ANOVA table and eta. Continue and okay. So this table, last button, measure of association, eta and eta square. Here this eta square is what is effect size. I will show you once again. Okay. Once again, I'm showing you how to calculate. First of all, you need rank data. Okay. Analyze. And then you go to compare means. And in compare means, creating problem. Analyze. Compare means. In this you supply this rank of self-efficacy as dependent variable, meditation as independent variable. And then in option, you select ANOVA table with eta. Continue and okay. So this I have taken here. So I need this table, this particular table. This is eta squared. Yeah, this is effect size. 0.586. And you can calculate it using this formula also. Effect size is equal to h upon n minus 1 under root n minus 1. So what is h? What is the value of h? Value of h is here. Yeah, 7.623. H is 7.623 divided by n is 14. 14 minus 1, 13. So if you solve it, 7.623 the 7.623 divided by 13 is 0.586. 0.586. So this is the same value which you find here, 0.586. Okay, so this is how you write. As observed from table 12, effect size epsilon squared written here as eta squared is 0.586. Alternatively, effect size is h upon n minus 1. From table 9 and 10, Kruskal-Wallis h is this, n is 14. Effect size is 7.26 upon 13 is equal to 0.586. This means the meditation program is able to explain 58.6% variance in the self-efficacy of the practitioners. Means the self-efficacy, 58.6% of the self-efficacy can be explained by meditation program. So meditation program is responsible for 58.6% of the self-efficacy of the practitioners. And it is quite a good size of effect size. DF is equal to 11, DF is a measure of sample size. DF is measure of sample size. It is normally n minus 1, but here it shows sample size only. I think I have come to the end of my presentation, and it is time to say thank you to all and welcome any query in addition to the queries already which you put in the chat. Or so thank you all. The time was short, and I know that it might have been difficult for many of you to assimilate it in such a short span of time. The content was quite heavy, but nevertheless, this is what I could do. Thank you all. Thank you, madam.
Thank you, sir.
Now I hand over to you.
Yeah, dear participants, if you have any queries, you can unmute and ask your question.
Yes, most welcome.
Good afternoon, sir. Sir, I'm Albino. I just wanted to ask you, what is the maximum sample size on which we can do this test?
Pardon?
What is the maximum number of sample on which we can do the test, sir?
I'm not getting the voice is broken. Voice is broken. Can you?
Sir, can you hear me now?
No, I can't listen properly. Please write your question. Please write your question in the chat box. Please write. You are not properly audible. What is the maximum sample size to use Kruskal-Wallis? Please note, all of you. There is no maximum size. Generally, it is believed that people believe that non-parametric tests are used when the sample size is small. This is wrong. You can use non-parametric test even if your sample size is 1000. There is no upper limit to sample size in the use of non-parametric tests. Let it be Kruskal-Wallis, let it be chi-square. Large sample size does not mean that you cannot use non-parametric test. But large sample size means that you will use parametric test provided the assumptions of the parametric tests are met. So whenever you go for testing of the assumption, okay, the whole problem is created because people do not use People do not examine, they don't have the habit of examining the assumptions of the parametric test. So they essentially link the use of parametric test to sample size. Whenever there is a greater sample, go for parametric test. Yes, go for parametric test, provided the assumptions of the parametric test they are met. But if the assumptions are not met, you don't have any alternative, you have to go for non-parametric test. So there is no upper limit to sample size as far as use of non-parametric tests are concerned. There is a limit. Lower limit is there. Certain tests, for example, Kruskal-Wallis test cannot be applied when you have total, say, 5 sample size total. All the 3 groups they combined in a combined way have less than 5 sample size. Then probably you cannot use Kruskal-Wallis test. Any other question, please? See, I am conducting at least one program. Today itself, I am having one program from 4 to 5:30. So if anyone is interested in attending my programs, then I can give information, but how to give information, I don't know. So I will share my email ID. This is what I can do.
Hello. Hello.
Yes.
डॉक्टर साहब मेरी आवाज आ रही है?
I am giving you my email ID. sktyagi.sk@gmail.com. sktyagi.sk@gmail.com. ये मेरा email ID है. If anyone is interested in getting information, he or she may write to me. Thank you.
Sir, there are a few questions in the chat box. When there are 2 independent groups, which one will be better? Mann-Whitney test or Kruskal-Wallis test? Why? When there are 2 independent groups, which one will be better? Mann-Whitney test or Kruskal-Wallis test, and why?
Kruskal-Wallis test is one, and which one is the another?
Mann-Whitney test, sir.
Mann-Whitney test. See, Mann-Whitney test is used when we have 2 groups. When we have 2 groups. If you have just 2 groups, okay, then you can use Mann-Whitney test. But suppose there are more than 2 groups. Okay, you have 4 groups. Then also those who do not know what is Kruskal-Wallis test, they generally use Mann-Whitney test. Okay, so you can.
Thursday రోజు మనం
I don't know who muted me. Say, whenever you have more than 2 groups, say 3 groups or 4 groups, 5 groups, okay, even then people use Mann-Whitney test. They use, for example, there are 4 groups, so there can be 6 comparisons, so they will use 6 Mann-Whitney tests. But that is wrong, because this will increase alpha error. And as I discussed while discussing the post hoc test, alpha error is adjusted. If instead of using Kruskal-Wallis test, you are using 6 Mann-Whitney test, then you may commit a mistake. You are committing error. You may reject null hypothesis, and the null hypothesis should not have been rejected. Sir, when ANOVA and ANCOVA are to be preferred, what type of data they are to be done? Say ANOVA and ANCOVA are preferred, okay, when you have the assumptions are met, assumptions are not violated, then you can go for ANOVA and ANCOVA, provided the assumptions are met. If the assumptions are not met, then you have to go for non-parametric test. For example, let us take an example of ANCOVA, analysis of covariance. So there is a test, non-parametric. People are not aware of that. There is a quad rank test, ANCOVA. Even factorial design ANOVA has non-parametric counterpart, but people do not know. Align rank test, align rank ANOVA or art ANOVA is non-parametric counterpart of factorial design ANOVA to ANOVA. Any other question, please?
Hello. Hello.
Hey.
Hello, sir. Good morning, sir. This is Dr. Anurag Pandey.
Hey.
Sir, Dr. Anurag this side. Sir, my question is this, that we are talking about the assumptions for parametric test. So there is also one assumption that the data should be taken, the samples should be taken randomly. So many times in social science research or in the marketing research, what we do, we take the data in a non-parametric or in a non-random sampling. So can we go with the, if the other assumptions are fulfilled, but this assumption where the data is being collected non-randomly, can we go with the parametric test?
See, I realize it that in social sciences, it is very difficult to have randomized experiments and randomized sample selection. But
yes, sir.
But we must at least have some kind of randomization. For example, when you are conducting experiment, you can assign the treatment randomly. Suppose you are taking three students, three group of students, okay, and therefore there are three treatments. So you can assign these three treatments randomly to three groups. Don't give one group deliberately. Don't give treatment one to group one. Okay. So there are ways in which you can reduce the bias, although you cannot take perfect random sample in social sciences. This is true.
So can we do this one thing, that we have taken a data from maybe from 12, maybe for example, we have taken data from thousands respondents, and randomly we have taken 750 out of that. So can it be applicable in that case, random? First we have taken a data
but
from 1,000 respondents.
You have to, suppose you are randomizing at the level of this, suppose there is a multi-stage random sampling. At different stages, you select the district randomly. Then from the district, you select the block randomly. Okay. Then from the block, you select village randomly. But you cannot select the household randomly. So
yes.
you have taken every care to select the sample randomly. But perfect randomization is not possible. But you have to take care that your sample is not biased. Okay. And you have taken all care which is in your capacity to make your sample selection unbiased and representative of the population.
Yes, sir. My simple question, another question was that only, that first we have taken the data maybe from 1,000 people, and after taking data, we are taking 500 out of that. We are taking 500 samples out of that 1,000 randomly, because it was not possible on that time. But now we are taking 500 respondent randomly. So can it be considered as a assumption for the parametric test?
I think I have answered this question. Okay.
Yes, sir.
I have already answered this question.
Thank you, sir. Thank you.
Okay, thank you.
So there's a question in the chat box. Can we tell influence based on mean analysis regarding dependent and independent relationship? This is a question.
Yes, madam. Dependent and independent.
Relationship, sir.
No, you want relationship between two variables?
Question is, can we tell influence based on mean analysis regarding dependent and independent relationship?
I see. I do not know what do you mean by mean analysis. What is mean analysis? What do you mean by mean analysis? I am not aware of this term, mean analysis. Actually, when you are comparing means, is it mean analysis? We are analyzing means. I don't know the exact connotation of mean analysis. What do you mean by mean analysis? Here also we are comparing mean ranks. So it is an analysis of the mean ranks. But we are comparing groups in terms of mean ranks, because mean here is not used in non-parametric analysis. We are using mean ranks. This is rank-based analysis. So can you explain me the meaning of mean analysis? Okay, madam.
Yes,
Let us stop at this point. No?
Hello.
Yes, sir.
May I please? Hello.
Hello.
Yes, sir, very good day to you. This is Shamim Firdaus. With kind permission
Huh?
from you, may I please ask my query?
No, I'm getting you. I'm not getting you what you are saying.
Can you put your question in the chat box, sir? You're not audible.
नहीं आवाज नहीं आ रही पूरी तरीके से ना, क्या कह रहे हैं?
Yeah, Jayashree, please, can you propose a formal vote of thanks to Tyagi sir?
Yes. On behalf of Department of Business Management, I am privileged to propose the vote of thanks for the session. The session focused on non-parametric tests, the characteristic features and assumptions of Kruskal's-Wallis test, one-way ANOVA by ranks. Then sir also spoke about a new non-parametric living test for equal variances. Thank you, sir, for your detailed explanation with proper live examples using SPSS. Thank you, sir. Thank you for your valuable time. Thank you.
Thank you, madam. Thank you so much.
Thank you, sir.
Thank you, sir. Professor Tyagi sir, thanks for being a part of this 10-day program on behalf of RBVR Women's College. We'll be in touch with you, sir. Thanks a lot. The session was excellent. We're getting good feedback from the participants. Thanks for your time, sir.
Thank you, madam. Thank you so much.
Thank you, sir.
Thanks.